This is pre-calculus 1, analytic geometry. We're going to begin our discussion on fundamental concepts and principles. The beginning of analytic geometry can be traced back in the 17th century. In 1637, the French mathematician and philosopher René Descartes, who lived from 1596 to 1650, introduced a device called the Cartesian coordinate system, named in his honor. Pierre de Fermat's Introduction to Loci, written about 1639, was clearer and more systematic than Descartes' La Geometry. However, Fermat's work was not published during his lifetime. But history was not good and fair to Fermat, that most of the credit and honor for the development of the coordinate plane with now the familiar x and y axis were given to René Descartes. So René Descartes was given the title Father of Analytic Geometry. Okay. Now, it is by means of coordinate systems that algebra or algebraic methods can be applied in the study of geometry. That is, equations in algebra can be represented geometrically and vice versa. So this led to the union of two distinct mathematical disciplines, algebra and geometry, into a separate field called analytic geometry. So what is analytic geometry? So when you say analytic geometry, it is a unified algebra and geometry dealing with the study of relationships between equations and geometric figures by means of algebraic processes and geometric properties in relation to a coordinate system. Before, for instance, a straight line couldn't be represented by a line, no? So, and in the same way, a geometric figure like a straight line couldn't be represented by algebraic form, meaning in terms of equation. But because of this René Descartes' Cartesian plane, so mathematicians were able to connect algebra to geometry, geometry to algebra. That is, equation can be represented geometrically, like line by what? By straight line, and that straight line can be represented mathematically using equation, which is a linear equation in x and y. Like for instance, 2x plus y equals 5. That is what? A straight line geometrically can be represented. Okay? There are two divisions of analytic geometry: plane analytic geometry and solid analytic geometry. So what is the difference between the two? Plane analytic geometry covers the study of points, curves, and planes in a two-dimensional coordinate system. So what are those commonly used coordinate systems? We have what we call Cartesian plane. So look at the figure. Here, a polynomial curve is traced, no? So we can trace a curve in a two-dimensional coordinate system like in this Cartesian plane. You can even draw, let's say, parabola, no? You can plot points. You can draw plane figures like circle, rectangle, polygon, okay? Another one, we have what we call a polar coordinate system. In this polar coordinate system shown, a heart is what? Is drawn. We call this cardioid, okay? And this is given by the equation R equals 3 minus 3 sine theta. So that is just an example, no, of a cardioid traced in a polar coordinate system. So the second one is what we call solid analytic geometry, but this division is not covered by our syllabus. We will be focusing only in plane analytic geometry. But what is solid analytic geometry? So this division covers the study of points, curves, surfaces, and solids in space. So meaning all those that we study in plane analytic geometry are covered also in solid analytic geometry, plus solids, no? Because this is in space, we can draw solids. Now, when we say in space, it means in a 3-dimensional coordinate system. So here we have a rectangular coordinate system. Showing in this rectangular coordinate system, 3-dimensional, we have a line segment connected by 2 points, and it is floating, no? As you can see, okay? So there are 3 dimensions, x-axis, y-axis, and z-axis. Another one, we have a surface drawn in a rectangular coordinate system. We call this hyperbolic paraboloid. So this is a surface called hyperbolic paraboloid. Okay, guys? There are other 3-dimensional coordinate systems commonly used aside from rectangular coordinate system. We have what we call cylindrical coordinate system and spherical coordinate system. If you're going to take BS Math, for instance, or engineering, you will be encountering these other coordinate systems in space, okay? So coordinate, what are they? So rectangular coordinate system, cylindrical coordinate system, and spherical coordinate system. Again, we are solid analytic geometry is not part of our syllabus. We will be focusing only on plane analytic geometry. Now, we will be discussing, or we will be talking about later the very important device discovered or invented by René Descartes, and actually invented also by Pierre de Fermat. An important concept dealing with that, or that will lead to rectangular coordinate system in a plane, is what we call directed line segment. So when we say directed line segment, it is a line segment in which one direction is chosen as positive and the opposite direction as negative. Okay, so meaning it is a line segment with sign, no? When it comes to their value, the line segments values, no? When you say directed line segments, so again, directed line segments, the values can be negative, can be positive, okay? And the measure of the length of a directed line segment, the signed measure, is called directed distance. So a directed line segment, when you measure, so the signed measure is either negative or positive. Let us consider the line segment below with points A, B, C, with A at the left endpoint and C at the right endpoint, meaning B is in between. If we're going to consider the directed line segment AC as positive, then the directed line segment CA is negative. If a line segment is directed, you're going to put arrow on top. That is our notation that we are going to use in directed line segment. So from this figure, we can have the following relations. So one is that the directed line segment AC, because that is chosen as positive, so that is equal to negative of directed line segment CA. Alternatively, we can write this as directed line segment AC plus directed segment CA, and that is equal to 0. Okay. Furthermore, we have the following relationships. Directed segment AB plus directed segment BC is equal to directed segment AC. As you can see from the figure, I can also have directed segment AC plus directed segment CB is equal to directed segment AB. And then we have directed segment BA plus directed segment AC is equal to directed segment BC. And of course, there are other relationships that we can get from here and form, no? So these are just samples. So let us have the following example. If A, B, and C and D are 4 consecutive points on a directed line with directed segment BC equals 6, directed segment CD 4 units, directed segment ED 12, find the following expressions involving directed segments. So let's draw the figure. So we draw a directed line containing the following points, A, B, C, D, with A to the left, and then followed by B, then C, and then D. No? So from the given information, we have CD is 4, BC is 6, and AD is 12. So we can now find the value of this expression involving directed line segments. Okay. So what is AB, guys? So AB is equal to 2, no? Because if this is 12 and this is 10 from B to D, the remaining part here is 2 plus CD. So CD is taken as positive also, no? Because that is from left to right. So the value is 4 minus CA. But CA is from what? Right going to left. So that is negative. So CA is 6 plus 2, so negative 8. Okay. So the value is equal to 6 plus 8, that is 14. So this is the value of this expression involving directed line segment. So let us have the second one. Product of directed segment AB, AD plus 3 times B directed segment BA and 2 times directed segment DA minus directed segment BD. So looking at the figure, AD is positive, no? So that is 12 plus 3 times. What about BA? BA is from right to left, so negative. So that is negative 2 because this is of length 2 taken directly, so that is negative 2. And this is multiplied to what? To this difference. Okay? So we have 2 times what is DA? That is also negative, no? Negative 12 minus BD. BD is positive 10. And the first factor is equal to 6. The second factor is equal to negative 32. Am I right, guys? Or 20 or 34. So again, the first factor is equal to 6. The second factor is negative 34. 6 times negative 34 is negative what? 204. Am I right, guys?
Yes, sir.
Yes,
Okay.
sir.
Yes, sir.
So we're now ready to discuss rectangular coordinate system or simply Cartesian plane. So other term, Cartesian coordinate system. So when we say rectangular coordinate system, it is a coordinate system in a plane consisting of two perpendicular lines intersecting at a common point called the origin. The perpendicular lines that intersect at the origin are called coordinate axes. These are x-axis and y-axis. And these coordinate axes divide the plane into four regions or compartments. Each compartment is called a quadrant. So let us illustrate that. So we have this Cartesian plane consisting of x-axis and y-axis intersecting at this common point called the origin. And that origin has coordinates what, guys? Anong coordinates ng origin, guys? So equals what, guys? 0, 0. Am I correct, guys?
Yes, sir.
Yes, sir.
Okay.
Yes.
Now, this first compartment, upper right, we have what we call first quadrant, and the sign of the coordinates are positive, positive. In the second quadrant, this is left right portion of this Cartesian plane, we have negative, positive, second quadrant. Third quadrant is here. So just below second quadrant. So quadrant 3, negative, negative. And then to the right of it, quadrant 4, which is positive, negative. Okay? Okay, we can plot points. No? We can even draw figures in this Cartesian plane. But before we can talk about that, so we recall what we call ordered pair of numbers. So from algebra, how do we define this? It is a pair of real numbers in which the order of occurrence of numbers matters. Okay? So, for instance, 4, 2, so that is an example of an ordered pair. Negative 5, negative 1/2, negative pi, 2, 0, 3. So these are examples of ordered pairs of numbers. Now, two ordered pairs of numbers are equal. Let's say the first is AB. That is equal to the ordered pair CD if and only if A is equal to C and what, guys? And B is equal to D. Okay? We are going to use this notation to denote or to represent a point in the Cartesian plane. So we say that XY, for instance, if this is our ordered pair, so this ordered pair represents what? Represents a point algebraically. And when you say algebraically, that is analytically. Okay? So what about geometrically? How do we denote or express a point? So we are going to make use of a dot. So we call this dot, no? So this point is called a dot. It represents what, guys? Represents a point geometrically. Okay? Is that clear, guys? Now, let us consider this Cartesian plane. Y-axis, x-axis. Let's say I have a point here, represented by this dot. A point can be named by a capital letter, let's say P, and then making use of ordered pair, x, y. So that's our point. If you take the directed distance or a scaled or signed distance of P from the y-axis, we have what we call abscissa. Clear, guys? So we call this directed distance what, guys? Abscissa. So meaning, this x, no? Am I correct, guys? And then the vertical distance directed, because can be negative, can be positive, of P from the x-axis is called ordinate. Okay? So in this ordered pair, we call the second component the ordinate. Let us have the following examples. So let's say we're given the following heading, point, abscissa, ordinate, and then finally we have location. Location means either quadrant 1, quadrant 2, quadrant 3, quadrant 4, or x-axis, y-axis. Clear, children?
Yes, sir.
Yes, sir.
So let's say I have a point 2, -5. What is the abscissa? The first component or the first number here. And then the second component is -5, no? So that's the ordinate. Location, that is in fourth quadrant. Quadrant 4. What about if I have -3, -1/2? Oh, abscissa is -3, -1/2 is the ordinate, and this is located in third quadrant. If I have 5, 0, 5, 0. So abscissa is 5, ordinate is 0. So it's neither in any of the quadrant, no? So what is the location, guys?
X-axis.
X-axis. So in other words, if the ordinate is 0 and you have a number here, it is located on the x-axis. What about if I have -pi? Or what is the location, guys? Quadrant 2, no? And then -pi is the abscissa, 4 is the ordinate. A last one. 0, -3/2. So 0 abscissa, -3 halves coordinates. So this is located along the y-axis. Correct, guys?
Opo.
Yes, sir.
This is located along the y-axis. So let's say we're given this problem. Draw a triangle with vertices A for -1, B -5, +3, and C coordinates, we have -2, -2. Okay? So first, we're going to plot the given points now. Let's draw a Cartesian plane. Y-axis. 1, 2, 3, 4. So let's say this is the x-axis. Okay, guys? X-axis. 1, 2, 3, 4, 5, 6. -1, -2, -3, -4, -5, -6. Then 1, 2, 3, 4. Okay? -6, -3, +3, +6. Then 2, 4. -2, -4. Let's now plot. For -1, for -1. Check if I position the point correctly. Huh? -5, +3. 1, 2, 3, 4, 5. -5, +3. Clear, children? Then the last one, -2, -2. Then we connect to form a triangle. Okay, guys? Then we have here, sorry. And then we have this is the triangle, okay? So let's name them. This is point A, point B, and point C. Any question with this? So that's how to draw a plane figure called triangle in Cartesian plane. So let's now start talking about a formula that can compute the distance between 2 points. No? We have distance between 2 points. So letter A, we have what we call horizontal distance. So let's say I have this segment. And I want to know the length of this segment, meaning the distance between this point A and this point B. And let us assume that this is x sub 1 and this is x sub 2. If you get the distance between points A and B, all you have to do is to get the difference between these two coordinates, okay? So distance of horizontal, distance of 2 points lying horizontally, we have x sub 2 minus x sub 1. To make sure, if you're not sure of the sign, so take the absolute value so that it is guaranteed always positive. Okay, guys? Because we are not after directed distance. We are after the positive or just the actual distance. Na? What about if we have vertical distance? For vertical distance, we have this, for instance, line, segment. Let's say this is point A and point B. This is Y2 and this is Y1. So how do we get the distance between these 2 points lying vertically? Get the difference of the one that is on top, then minus the one that is below. Okay? Then to make sure, take the absolute value. And generally, we have what we call letter C. This is any location of the points. Okay? This is any distance, in other words. Now, for any distance, we have, let's say, this point, no? And another point here. Generally, it's inclined, but it can be any. So let's call this P1 and let's call this P2. Coordinates x sub 2, y sub 2 for P2. And for P1, we have x sub 1, y sub 1. Now, to get the distance between the two, you are going to extend this point to the right. Then here below, you will be able to come up with a right triangle. And then you are going to apply for the measures of the sides, the three sides, Pythagorean theorem, okay? And you will come up with this formula. We have square root of what? X sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. Get it, children? We call this what, guys? What is this, guys? That is called
Distance formula.
Distance formula.
distance formula. Okay? So let's say we're given this problem. Find the length of the line segment connecting A for -5 and B -3, -8. Now for this type of problem, no need to draw because we can easily determine by applying the formula, no? So although there are problems that you need to draw or illustrate in order for you to analyze the problem. Okay, guys? So in this case, you can take A as our P1, you can take B as our P2. But any of the 2 points can be taken as P1. It doesn't matter. Arrange again, you can take A as your P1, B, P2. But any of these two can be taken as your first point. So we have distance between them is the length of the line segment connecting A and B, no? So we have x sub B minus x sub A, quantity squared plus y sub B minus y sub A, quantity squared, okay? So substituting these values respectively, we get -3 minus 4 quantity squared plus -8 minus -5. So it is now +5, right? So quantity squared. So this is equal to, what is this? 7 negative square root 49 plus -3 square root +9, no? So finally, we have a square root of 58. Am I correct, guys?
Yes, sir.
Opo.
Okay, so square root of 58. Another thing that we can do on a line segment is that we can determine its middle point. Okay, so let's say we're given this segment. By the way, what is a midpoint of a line segment, guys? What is a midpoint of a line segment? Guys,
half of the
it is a point
is the point that is
dividing
dividing the
dividing
line
what?
segment.
Dividing the segment into
Two equal parts.
Two.
two equal parts, no? Into two equal parts. Okay, guys? Yeah. So let's say we have this line segment. And this is my point, the middle point. So let's label them. So let's say this is point M, where point M having coordinates x sub m, y sub m. And then the other points, we have this first endpoint, P1, and second endpoint, P2. P1 has coordinates x sub 1, y sub 1. When I say P1, let's understand that coordinates x sub 1, y sub 1, huh? And if I have P2, coordinates x sub 2, y sub 2. So even I don't say x sub 2, y sub 2, and I say P2, so I mean with these coordinates. Now to have x sub m, what is the formula for x sub m, guys? What is x sub m?
Sir, x sub 1 plus x sub 2 divided
X
by
sub 1, all we have to do is to add the x coordinates, no? Then divide by 2. What about y sub m?
Y sub 1 plus y sub 2 over 2.
Okay. Okay. We call this two midpoint formula, no? Or the coordinates of the midpoint. Collectively, midpoint formula. Okay, children? Yeah. Like for instance, if we have, let's say, this problem, find the center of a circle whose endpoints of the diameter are -2, -7, and 8, 3. Okay? So again, this can be easily solved, no? When you say center of a circle, having endpoints of the diameter, this point, so it means the center is the midpoint of the line segment connecting P and Q, no? And the line segment connecting P and Q is the diameter. Am I right, children?
Yes, sir.
Yes.
So to get that center, let's call that H. So let the center HK be the center. So we can apply this midpoint formula. So our X sub M is H. So that is X sub P plus X sub Q. Am I correct? All over 2. Giving what? What is that? X sub P2 plus 8, right? All over 2, no? What is H, guys?
Sir, 5.
5. What about K? K is equal to Y sub P plus Y sub Q. All over 2, giving -7 plus 3. All over 2. And that is
Negative.
2. No? So therefore, what is the center? 5, -2. So if you're going to plot these points, P and Q, connect them. So 5, -2 will lie at the middle of that segment. That segment PQ represents the diameter of the circle. Clear, children?
Opo.
If you're going to collect segments, at least 3, you will form a closed region, not possible, but of course not all the time. But if you have a collection of 3 or more segments, you can possibly form a closed region called a polygon. Clear, children? So let's recall polygon. Bounded by what? By segments, no? Enclosing a region. Now, at least 3. What is the minimum number? 3, no? And that polygon form is called what? Triangle. Then we have quadrilateral, pentagon, hexagon, octagon. What else? Nonagon, no? And so on. If I have a polygon like this, guys, we call this polygon convex. Am I correct, children? If I have a polygon like this, what is this, guys?
Concave, sir.
Non-convex or concave, no? Okay? So we will be considering convex polygon. But you can also find, of course, the area of an non-convex, but you have to divide this so that you will be able to form what we call convex, because the formula that we're going to have applicable to convex. Okay, children? So we have what we call area of a polygon. Let P1, so when I say P1, understood that the coordinates x sub 1, y sub 1, ha? So we agree on that. P2, P3, and so on, all the way to P sub n minus 1. And then the last one is P sub n. B vertices of a non-convex, of a convex. Of a convex polygon. So meaning this type, no? Okay. By the way, how will you know that it is non-convex? There is an interior angle, at least one interior angle that is what? More than 180 degrees. Okay, guys? So again, let P1, P2, P3, all the way to Pn be vertices of a convex polygon arranged arranged in counterclockwise direction. What does it mean? Guys, from right going to left, no? Then down, up, and so on. Am I right? Okay. So it means the polygon here has, since it has n vertices, so n points, it has n vertices na. Okay? The area of the polygon is given by, as long as non-convex, as long as convex polygon. The area of the polygon is given by this formula. Area of a polygon of n vertices is equal to 1/2 of this array of numbers, no? X sub 1, y sub 1, corresponding to the first point. Second column, x sub 2, y sub 2, corresponding to the second point. Third column is x sub 3, y sub 3. And then all the way to x sub n minus 1, y sub n minus 1, then x sub n, y sub n, and then finally, the last is the first point that you're going to consider. Clear, children? And this array of numbers, enclosed in braces, we are going to agree that it means this difference. So we have first, sum of products of these numbers diagonally, no? X sub 1, y sub 1. No, x sub 1, sorry. X sub 1, y sub 2. Then x sub 2, y sub 3. Plus x sub 3, y sub 4. Plus dot, dot, dot. Yan. X sub n minus 1 times what? Y sub n, no? Plus the last one, x sub n, y sub 1. And then subtracted from the sum of products, similar but going up. y1 times x sub 2. y1 x sub 2. So then plus y sub 2 x sub 3 plus y sub 3 x sub 4 all the way to what is the next one, guys? Anyone? Y what?
Y sub n minus 1 times x sub n.
Y sub n minus 1 x sub n. Then the last one, y sub n x sub 1. No? Okay? That's it. So that's what we mean by this array of numbers. This is not a matrix, although similar to matrix, no? But it is just a special notation just for this purpose. Actually, this notation is not universal, that it means like this. We define it this way. We agree on this. Clear, children? And it was proven in mathematics or in analytic geom that this works for area of a polygon or convex one. Clear? So for instance, if you have a problem like this, find the area of a triangle with vertices at A, five, 3, B, -1, -3, and then C, +1, -5. Okay? So first, let us draw the triangle so that we know the first point and then the next point in counterclockwise with the first point that you are going to consider. Any of the points A, B, C can be considered your P1. But as long as your second point is in counterclockwise with it. Okay, guys? So we have this triangle. Let's say this is the x-axis. Okay. The y-axis. One, 2, 3, 4, 5. 1, 2, 1, 2, 3. So this is 3. So this is -1 actually, -2, -1, -2, -3, -4. Plotting the points. 5, 3, 5, 3. Somewhere here, no? Then -1, -3. -1, -3. Around here. The last one, 1, -5. I have to extend the y-axis. This is -5. 1, -5. Am I correct, guys? So this is our triangle. Connect. Okay. And what is the area of this triangle? To get the area of the triangle, we apply the formula. So what's the formula, guys? Area of triangle, or you can write a sub 3. 1/2 of what is our considered first point, guys? This is point A, point B, point C. If we consider our first point as point A, so we have 5, 3. What is the next point in counterclockwise with that? Counterclockwise, right, guys? So it is the B, not according to letter. It so happens that it is correct alphabetically, but what we mean by point 2 is the next point in counterclockwise. So it so happens that it is the B. -1, -3. And then what else? 1, -5. Do I have to stop here, guys? Or is one more column?
One more column.
1. We end up with what? With the first point that you have chosen. Always do like that, okay? So this is equal to diagonal products going down. 5 times -3 plus -1 times -5 plus 1 times 3, then minus going up. 3 times -1 plus -3 times times 1. And then the last one, -5 times 5. Am I correct, children? What is the first one equal to? You can use calculator. -15 plus 5 plus 3. Is it -7, guys?
Yes, sir.
The area must be positive. If you get a negative, there is something wrong. Either your arrangement of points not correct. Okay? Then -3 minus 3 minus 25. Is it -31, guys? So positive 31 now, okay? Am I correct?
Yes, sir.
Because supposed to be minus negative, so positive 31 now. What is now the area? Guys,
12 units, sir.
24 divided by what? Okay? So I think I missed the 1/2 in front here. One-half of so it is 24 divided by 2, so that is 12. What is the unit, children? Guys, 12 square units. Am I right? Because this is area. Is this clear, children?
Yes, sir.
Yes, sir.